this? What method, what approach should we take? Yeah, make a chart. Okay, we made a table last time. So the table said the following. We first identified the 4% solution in this row, then the 18% solution, and then the final mixture at the end. Okay? In the first column, we put the number of milliliters. In the second part, we put the percent acid. And in the third column, we put, this is the number of milliliters of acid. Okay? And remember what we talked about last class. We talked about the fact that when you multiply these first two columns, we went over exactly how to do this. Okay? You take the number of milliliters times the percent of acid, you'll get the number of milliliters that are consisted of just acid. So if you have 100 milliliters and it's 50% acid, you have really 50 milliliters of acid. So you just have to multiply across. Now, the question becomes, what are our values for the first column? That's the tough one. What are the values? How many milliliters of the final mixture do we want? Chris? Yeah, so that goes down here, right? We want 25 milliliters of the final mixture. But the question is, we don't know what these are. We don't know what the next two numbers are. The question asks us how much of each acid is needed. Okay, how much of each acid is needed? So that's what we're trying to figure out. So what can we put in those spots if we don't know what they are? X for sure, and not Y. 25 minus X. Because the whole thing is 25 milliliters. Whatever the first one is, subtract that from 25, you get how much is left of the second one. Okay? At this point in time, we list our acids as decimals. What are the three decimals, Jared?
0.04, 0.018, and the last one is 0.25.
Good. Okay? Remember, percent, move it over 2 spots. Per means over, cent means 100. Over 100.
12.
Oh, okay. I picked 25, I listened. Means I have confidence in you, Jared. It's a good thing. So 0.12. Final mixture is a 12% solution. There are 25 milliliters of it done. Okay? So what do we get here? What do we get in the third column from this? What does the third column look like, Ryan?
X times 0.04 for the first one. 0.04 X, and then you just, I don't know, 25 times 0.
Well, just, yeah, we can put in parentheses for now.
Yeah, and you just choose that for
Good.
I don't know what that is either. You just multiply that.
Yeah, 0.12 times 25. What do we get for that? It's going to be 2.5. 2.55 maybe?
This is 3. Yep.
Right, 2.55?
No, it's 3.
I'm sorry?
3, isn't it 3?
3.
5 and 2 is going to be 10, so it's not going to be 5.
Jared, what do you get when you multiply 25 times 0.12?
3.
3 even? Okay. Thank you. Sorry about that. I didn't understand what you're saying there. All right, so at this point in time, what do we know? What can we do with this table? Why did we make it? What's the reason?
Find out.
It helps us know what we're how to make the fractions.
Okay, so what does the equation look like, Chris?
So it would look like 0.04x plus 18 times
0.18.
oh, 0.1 times 25 minus x. And equals 3.
Good. Remember, people, remember. It's the third column that's important. The sum of the amount of acid in each solution must be the same as the amount of acid in the end. So if you put say there's 3 milliliters of acid out of here, or 2 out of here, and 1 out of here, that adds up to 3. That's what we need. So it's the last column that you're able to add together. At this point, what can we do to make this easier on us? What can we do to make it easier? Multiply by?
10, yeah, 10, or 100.
There it is. We want 2 decimal moves, right? Multiply the whole thing by 100. That'll move the decimal 2 spots here in these two. Make it easier. 100 is our LCD, by the way, if you noticed. Right? Because these decimals are really just over 100. That's what it means. Right? Isn't 18% just 18 over 100? So these are all over 100, really. That's why the LCD we're using in this problem is 100. Okay? Next, distribute and solve. I'm going to leave you to do the rest on your own. Now, once you get an answer for x, that'll give you one of them. Do 25 minus that to get the other. Okay? What else? What else work on? It's a mixture problem. Alright, so we've got the rate on the way up is 4, the delay at the top is 90 seconds, the rate on the way down is 5, the total time it takes is 270. Yeah? Let's write our 3 distance rate equations we could use here. Yeah, D equals RT. Let's start with, that's the general formula we're going to use. Okay? Let's write D equals RT for each of these scenarios. On the way up, D1 equals R1 times T1. But here's a question for you. The distance on the way up and the distance on the way down, what do you know about them?
That way down is faster.
The distance, not the speed.
Oh, this is the same distance.
Yeah, same, right? The way up and down? So D1 is equal to D2. But we could just call them D. Is that clear? There's no D1 and D2 anymore, so just call it D instead. The rate on the way up is 4. The time it takes on the way up is unknown. So that's our first formula. Second formula, D2 equals R2 times T2. The distance on the way down is the same as the distance on the way up, which is still D. The speed on the way down is 5.
Are we assuming that the time it takes is the same up and down?
No. Or else we would have said T1 equals T2, right? Think about it. If we're going at different rates and they're going the same distance, the time can't be the same. It'd be like taking the 6 train instead of the 4 train between 86th and 42nd, right? If you take the 6, it goes much slower, so the time is much higher. So T1 and T2 cannot be equal because the rates are different. So think about that logic there. Ian.
The third thing where it says R2 equals 5, why don't we just put D2 equals 5 times T2?
At the very bottom there,
That was the last one.
it says D2 equals R2 times T2.
Yeah, why, but if R2 is 5 minutes per second, why not just write it?
I did. I put it on the next line. Look at the next line, Ian.
Oh, okay, alright, because I thought it was like one for each one.
No. This is one formula, and then that's the second formula right there. Okay? Now, with this information, it is not enough to solve. We have to think about one more thing total. One more thing we have to think about. The delay. Very good. So, tell me somebody, please, about the time it takes for this entire thing. Okay? Tell me about the time it takes for the entire problem here.
How long is the delay?
The delay is 90 seconds. It says it right there.
Alright, so it's 270 plus 90 plus like T1 is how long it takes you up and down.
Nope.
What are we looking for?
The relationship of the time up and down, but that is not correct.
It's not.
You're making a mistake. Jared?
The total time, if you subtract 90, it adds up the time spent traveling.
Yes. So the time up and the time down, oops, that's a plus sign. The time up and the time down is not 270 seconds because we wait at the top for 90 seconds. So it's minus. You said plus, Ryan, and then you said plus T1. Okay? Yeah, I am. This is the total time, T1 plus T2, of the trip itself. The 90 seconds is not part of the trip, so we have to take that away from that.
Alright.
Okay? Alright. So at this point in time, what can we do? What can we do, people? Yeah, so solve for T1 and T2 in those equations up top and substitute them in. It's the same process every time for these kinds of problems. So solve for T1 and T2, the arrows where you see those, and plug them into this formula. Bless you. What happens now? What can we do? Find A. Yeah, what is it?
20.
Good. The whole equation by 20, yep, everything. Which is easy to do, because 2 times 18 is 36. Put the 2 zeros on the end. Okay? Ian?
Oh, okay, wait, no, I just did it like without writing everything out like that. I mean, like, yeah.
So again, this is your time relationship here. You plug in the d over 4 and the d over 5 for them. Carry them down. Multiply by 20 because that's the LCD, which gives us 5d plus 4d equals 3600. Combine the like terms to 9d. Divide by 9, you get the distance is 400. And what does the problem ask us for? What did I say the actual wording was? The height of the tower. So that's your answer. You're done. Because remember, d was the length of the trip one way or the other, which is the height of the tower. You do not have to double this. It's not saying how long is the round trip in distance. That would be 800. You do not have to do that. Okay? What are your units for d? Meters. Okay? Meters. These distance rate problems are all going to be like this, okay? You're going to have problems where you're going to see, you're going to have some relationships. Write all your givens. You should write this down. This is like your key to answering this. List your givens. List all of your d equals RTs that you can. So givens, d equal RT formulas, plural formulas. And then finally, if you have like a sum of the times to get the total time, or a sum of the distance to get the total distance, you'll have one or the other. Either they'll tell you like the 2 legs in the trip add up to this much distance, then it's d1 plus d2. But in this case, we have the total time. So you have to use the sum equation at the end. The sum of the times equals the total time, or you use the sum of the distances equals the total distance. It's one or the other usually. I'll tell you now that the mixture and this one will be probably 2 of your questions on the test already. Okay? I'll probably give you 4 and tell you to choose 3. What's that? No, on your test. These are definitely on the final too, these kinds of problems. Others. What other questions have we been having? What about the ones we did with like, one person can paint a wall by himself in 5 hours, but when helped by another person it only takes 3 hours? How long would it take that other person to paint the wall themselves? Remember those with the rates?
Oh, with the spray paint.
Yeah, the spray paint can. You want to do one of those?
Sure.
Yeah? No, yes?
Yep.
I mean, we could just do regular equations. You guys don't seem very interested in this one. What do you want to do to help you? Karen?
I'd like to go over this.
Okay. So, let's do a problem where it says... let me come up with a good one. Let's see if I can think of a good one here. Let's say Chris can paint his bedroom wall in 2 hours.
Are you gonna be like, how big is the wall?
It'd be like area and stuff. You have to use different formulas. Chris can paint his bedroom wall in 2 hours. But Chris's brother can paint his bedroom wall in 1.5 hours. How long would it take them to paint the wall together? So, again, for Chris, the time it takes is 2 hours. I know you don't have a brother, sorry, Chris. For his brother, it's just a scenario. It takes 1.5 hours. And then together is the question we're looking at. Together is the question we're looking at.
So how long would it take them to
Paint the wall if they worked on it together. And obviously it's not 3.5, right? You can't just add those numbers. It wouldn't be logical. The number has to go down, right? Okay? So, what do we do?
Average.
What do you got?
Average.
Average?
Yeah.
It wouldn't make sense. Think about it. If Chris's brother takes 1.5 hours and then Chris comes to help him, the average would be 1.75. So it would take more time? You know what I mean? It's got to be less than both of them for sure.
Oh, you think an inequality?
Make like an inequality?
Make an inequality.
No. No inequality here.
You define the variables.
What do you mean?
Make the time that Chris takes to do.
Make the time what?
Like Chris takes the wall equal X.
Okay, so give me something then more than that. Give me another statement.
The time that Chris takes to paint the wall is X. The rate. You define the rates.
Okay. So let's say this. After 1 hour, how much of the wall would Chris have painted? Okay. Okay. After 1 hour, how much would his brother have painted? How much? Where are you getting that?
That's 2/3.
Say again?
Isn't it 2/3?
Where are you getting that?
I don't know. I'm sure. Honestly.
Good, which is 2/3, but you're guessing. 1 over 1.5.
I know now because
Okay.
it's half an hour, half an hour, half an hour.
Or it's 1 over the number that you're given at the top. Make it easier.
Fractions.
See that?
Yeah.
1 over 2, 1 over 1.5. So, after an hour, and again, this does reduce to 2/3, by the way, yes, it does. But after an hour, the wall would already be completed, right? Half the wall by Chris and 2/3 of it by his brother, that's too much. So we know it's going to be less than an hour already. Right? We know it's going to be less than an hour already. How can we figure out how much of the wall they want to paint, or how time it would take to paint the whole wall by themselves, together?
Remember X and X is the time it takes.
So again, give me what you're saying.
I don't really have the amount Chris does and the amount his brother does over the time it takes. Or the time it takes over the amount that Chris does and the 1 hour over the time that it takes. So it's X is the time it takes and it's over the amount that Chris does and the amount that his brother does.
Okay, you're like halfway on the right track. Some of the stuff you're saying is right, some of it's wrong. Yeah.
I know there's the time it takes is on top. The numerator.
What time? The time it takes together or separate? What?
Together. The time it
Okay.
takes together to take the wall.
Good. Is on top.
Yes.
So, what would the equation look like then?
I don't know.
Okay. Let me just make this a little bit easier. I'll write an equation without using our words here. So, if you think about this, the hourly rate, right, times the number of hours would equal how much of the wall is done. Think about that logically.
Okay, so
If you work at 3 or an hourly rate, say you have like a third of the wall an hour, right? After 3 hours, you would have completed the wall. 1/3 times 3 equals 1. 1 wall is done. So that's your formula you need to use.
So it would be 1/2 times 2/3 hours made. No?
Nope. What are we trying to figure out? What are we trying to figure out? The amount of what?
Time it takes.
Time. So let's solve for number of hours. Okay?
Subtract the hourly rate and how much
Subtract. Really?
to divide.
Thank you. Come on. So the time it takes is here. Here's your rate. Here's your distance, really. How much of it's done. Believe it or not, I know distance sounds weird, but it is distance or amount. This is D equals RT. So solving for T, you're going to get D over R, right? Yes? D over R.
Do you know how big the wall is?
I'm sorry?
Do you know how big the wall is?
Do we know how big? Does it matter? No, it doesn't matter. It's all about proportions and fractions here. So, for a problem like this, we can say to ourselves, the amount of the wall that we want to be done in the end is how much? How much of the wall do we want to be done? 100% of it. We want to have 100% of it done in the end, right? What about the left-hand side of the equation? What can we make that?
1/2 times 2/3 times x.
Close, Jared. Close. What's that? Okay, we'll use the R1 and R2, which we have the 1/2 and the 2/3. How can we use them though? Jared was the closest so far.
That's the rate.
He said 1/2, 2/3, or times 2/3 times x. There's a little mistake there.
X over 1/2 times 2/3.
Close again, but not right.
Where are you from?
X is the time it's going to take them, right? In the end?
So if x equals the x equals 1 over 1/2 times 2/3. No?
Chris?
I don't know if this is like the same thing Jared said, but x times the quantity of 1/2 plus 2/3.
That's it. That's it. What did you say that was different?
Times.
Yeah, alright, so let's look at this. Watch. The time it's going to take them is x. Forget this for a minute if that confused you. The time it's going to take them is x each. Because they're working together. Chris, if you and your brother are working together and you spend 45 minutes, you're going to stop at the same time, right? So x is the same for both people. The rate that Chris is working at is 1/2. So this becomes 1/2 times x. Plus his brother's rate, which is 2/3 times x. Which is why Chris pulled out the x and said instead, which makes perfect sense, he said 1/2 plus 2/3 like that, and took out the x in front. Okay? That's what the kind of problem is. And here's the thing.
What's x?
What's that?
What's x? Is that how long it takes together?
X is how much time it takes together. Yes, exactly. Watch this now. And I said this in the other class yesterday. I might not have said it to you to make it easier. If we go back and rewrite this 2/3 as 1 over 1.5, remember earlier it was really 1 over 1.5 is 2/3? So if we did that, watch what happens. Write it as 1 over 1.5. Okay? And Chris, I know this was right down here, but for now, let's just say forget this for a second, okay? Watch what happens here. Come on. Off the screen. The quantity of time it takes Chris to paint the wall himself is right here, isn't it? Yes? The quantity of time it takes his brother to paint the wall is right here. The amount of time it takes them together is in the numerator of each, really. So this equation is really this. So if you want to write this in words, what's going on here is the numerator is always going to be the time it takes together. Always. The denominators are going to be the individual times each. Okay, the individual times each. So the time it takes them together goes in each numerator. The individual time it takes them goes in each denominator. And what's on the right-hand side? What does this represent? How many? 1 minute? 1 minute? Really?
Oh, that's one wall.
Yeah, the amount of things you're doing. One wall. The amount of jobs completed, really. Because if we're 2 walls, we would just change that to a 2. Okay? The amount, it's A-M-O-U-N-T, okay, of jobs completed. You can always use this formula. It actually is a correlation. Whenever you have a problem where there's 2 people working on the same job together, this will always work. So if you're told it takes them 16 hours together, but by yourself, Ian, it takes you 20 hours. 16 goes in these numerators, the 20 goes in one of the denominators, and the x goes in the other denominator to find out how long it would take the other person to paint the wall by him or herself, assuming you're painting 1 wall. If you're painting 2 walls, you put a 2. 3 walls and 3. What if it's not painting walls? What if it's, building a house? It takes a doghouse. It takes one person 3 hours to build a doghouse. So the 3 goes in the denominator in one spot. Together, though, with another person, it only takes 2 hours to build a doghouse. So both numerators are 2. How much time does it take these 2 guys or women or whomever, how much time does it take one of them to build by himself if they're building, or for 1 doghouse, or you can say 2 doghouses? So you can just put the time x here, and then put a 1 or a 2 depending. But the same formula always is used. Yeah. For this one, definitely, okay? Again, if you want to use that formula and just remember it, that's fine. It's always going to come up this way. Just like we did with the table with the percent acid, right? Remember? Rubbing alcohol, acid. I always use those 2 examples.
So even on the test, it would be quicker if we just figure out their rate, for example, this one was after an hour.
Yeah, but you know what else? Chris, this one, all you got to do is this. Ready? So time together over the time of person 1 alone, plus the time together over the time of person 2 alone, equals the number of jobs completed.
Also, we don't even have to figure out after an hour how much they complete, just what we got at first.
Well, it depends on what's being asked. For example, if you have the time it takes them together and you have 1 person by himself, you could find time 2 alone. If you have time 1 and time 2 alone, you could find time together. Okay? And it's always going to end up being how many jobs completed. Since we're looking at an hourly rate, we're looking really at 1 job. Okay? There are some problems that could ask you for more than 1, but I'm trying to think if I gave you one for your problem set or not. Like that with more than 1 job. Other questions? Besides word problems, any other questions? What should you know besides word problems? Tell me besides word problems. Okay? Adding and subtracting what? No. Qualities.
Not qualities, I'm thinking of a different word. But same.
Fractions.
Huh? And complex fractions.
Okay. Simplifying complex fractions.
Two different chapters. We also multiplying,
No, that was the previous
Find the
chapter.
LCD.
reducing the denominator.
So using LCD to solve equations. Me or you?
No, I pressed it.
Okay. No biggie. So using the LCD to solve equations. We also use the LCD to simplify complex fractions, remember. We also find the LCD to add and subtract fractions. So what's the key of this chapter again? Yeah, finding the LCD. Okay? So I'll give you an example. We have about 5 minutes. I'm going to write down an example of one of each of these that you could practice tonight, but you have your practice. So adding and subtracting can be something like this. Okay? Adding or subtracting that and then just simplifying. Complex fraction would be something like this. So the bottom one, clearly, what do you have to start by doing on the bottom one? Number 2. What would help you here? Because it is not obvious what the LCD is.
So factoring.
Yeah, good. Factor that trinomial on the bottom right, and what does it turn out to factor into?
X plus 2 x minus 1.
Yeah, which is exactly what the other denominators are, you noticed. Okay? A third example, that's adding and subtracting in complex fractions, solving equations with fractions. So something like this. Okay? Something like this. Find your common denominator. Common denominator, what would it be in this case? These are all factors, guys. Come on. There's really a 1 in front of all these. You can't just say that the x plus 10 is the same as the x minus 1. Chris? Takes 10.
I was going to say 20.
Not 20? When in doubt, what can you always do to find the LCD? Always.
You add the.
No, you can't add it.
Multiply the other, what's not in that. Multiply the first equation by x plus 10, and multiply the second equation by x minus 1.
Yeah, but you're ignoring the right-hand side of the equation stuff.
And multiply the right hand side by both of them.
Good. So you're saying the idea, but you're not still giving me the common denominator.
That's all 3 denominators.
Yeah. Right. It makes it a lot easier just to identify that and then multiply everything by that. And that, in the end, you end up getting what you're saying, but you would have missed the number 2 there, just so you know. You would have missed the number 2. Okay? So that's your LCD, the product of all the denominators. That's always a possibility. You can always do that. But I recommend that you always factor first and see what's missing to see what the product really is. That's really it. That's pretty much a lot, you know? I'm thinking that the test might be like a 75-point test, just because it might be shorter. It's only 4 sections. We went, pretty quick here. We didn't have a lot of time between the last test and now. Okay? I'll let you know on Tuesday, but either it'll be 75 points or 100. I have to decide this weekend and think about it.